The law will never be perfect, but its application should be just. To a person, that sentence is clear, but to a computer, the word "its" is a puzzle. Does it refer to the law or the application? Resolving that specific link is a challenge called anaphora resolution, and for a long time, it was one of the hardest problems in AI. Before 2017, the standard way to teach machines language was through recurrent neural networks. These systems process text the same way we read a book, one word at a time, strictly from left to right. This created a bottleneck. An AI couldn't process the 10th word until it finished the 9th. As sentences grew longer, the mathematical signal from the beginning of the chain weakened, causing the model to lose context of earlier words. Because this sequential process was tied to the length of the text, researchers were physically limited in how much data they could use. Broad linguistic context was simply too computationally expensive to learn. A team of researchers at Google realized that if they wanted to process language at a massive scale, they had to stop treating text as a chronological sequence. Their proposal was to abandon recurrence entirely, no more step-by-step reading. Instead, they built a system that relied on a single mechanism called attention. This is the transformer architecture. If you look at the encoder stack on the left, you'll notice something missing. There are no loops. There is no mechanism to feed one word back into the next. By removing those loops, the architecture can ingest an entire block of text all at once. It treats language as a set of simultaneous relationships, allowing the hardware to map the context of every word in parallel. This works through self-attention. Instead of looking at words in a line, the system creates a grid where every word examines every other word in the sequence at the same time to determine how they relate. To organize this, the transformer assigns every word 3 distinct vectors: a query, a key, and a value. Think of the query as the specific information a word is looking for, like a verb searching for its subject. The key is the label that other words broadcast. It tells the query, "I have the information you're looking for." When a query and key match, the model pulls the value. This is the actual data about the word that gets added to the model's understanding of the sentence. This system allows the model to mathematically calculate the relevance of every word in a sentence, regardless of how far apart they are. The model calculates this through a scaled dot product. It multiplies the query matrix against the keys of every other word to produce a raw score of how much attention should be paid to each relationship. Those scores then pass through a softmax function, which converts the numbers into percentages. This creates a clear map of which words are contextually important and which ones are just noise. To capture different types of relationships simultaneously, like grammar, tense, and meaning, the transformer uses multi-head attention. It runs this entire QKV process 8 times in parallel. Each of these 8 heads can focus on a different linguistic feature. Once they're finished, the model concatenates all those different perspectives back into a single, rich representation of the text. We can see the result in this visualization from the paper. These lines show multiple attention heads resolving a distant dependency, linking the verb making to the words more and difficult. Mathematically, the model has ignored the words in between and mapped the connection directly. By mapping these relationships in a single step, the system creates a complete web of meaning without ever needing to read the sentence in order. Because the transformer computes all words at once using matrix multiplication, the distance between any 2 words is effectively erased. The complexity drops to a constant, O of 1. This constant path length, powered by modern GPU hardware, is why AI scaled so quickly. The results were immediate. The big version of this model established a new state-of-the-art score of 28.4 Blue on English to German translation, outperforming every previous system after training for just 3.5 days. By proving that sequential processing wasn't necessary for understanding language, this paper provided the foundational architecture for the generative AI models we use today. Replacing the slow sequential logic of the past with parallel attention created an engine capable of mapping human language at a global scale.